It's my pleasure to give this seminar, and I start with a slide from Stockholm returning the invitation. Hopefully, for the time being, it will be a virtual invitation, but if you happen to be in town, I will be glad to show you around and to also give you a tour of our labs and arrange a seminar. So please write to me, and I would be happy to arrange that. So I will start. Today I will talk about structural dynamics of water using XFELs, because I think this is a topic that can be interesting for a lot of people here in the audience. So let's see. So this is the outline of the presentation. In the first part, I will discuss how we can use X-ray photon correlation spectroscopy at XFELs and measure ultrafast cage effects in water. And the second part, I will tell you about some experiments we did where we implemented a kind of optical Kerr effect using X-rays to look at transiently oriented water. But let me take a step back first and say, okay, why is it important to study water? There is a lot of reasons, especially nowadays when it comes to climate change and so on, that water can play an important role. And there's also a connection to life and so on, which can influence our understanding of water in biological processes. But from our perspective, one of the things that we are very interested in water is what people call the water mysteries. And Claudio briefly mentioned about that. So this is related to some anomalies in water. People think of water as a very ordinary liquid, but when you cool water, it starts to behave very different than simple liquid, like shown here in this graph, where you see the density and the temperature. And for a normal liquid, as you cool it down, it just becomes more dense. That's what you expect from your everyday experience. Whereas water has a maximum at 4 Celsius, and then it becomes less dense. And the same is true for compressibility, for example. If you imagine a normal liquid, like for example, alcohol or something, it becomes, as you cool it down, it becomes less compressible. So it's harder to compress it. Whereas water becomes more compressible. And this is like, there's been a debate about how to explain these anomalies. And one of the scenarios, exactly like Claudio mentioned in the beginning, he actually talked about this paper here from Poole et al. In Nature 1992, is related to the hypothesis that when you look at supercooled water, in other words, water which is liquid but below the freezing point, as you see here in this picture. So here you see a glass of liquid. When you throw an ice cube inside, it turns into crystal. And that's something you can actually do in your kitchen. So this is a metastable state. And this is now when you're going to these very cold temperatures that this divergence becomes the more pronounced in the supercooled state. So one of the scenarios that I was mentioning, it's that water consists of a mixture of 2 liquids, actually. One that is a high density, and when I talk about the density, I'm referring to the hydrogen bond network. So it's, in this case, very much disordered, although there is a debate of what is exactly the structure there. And then a low density, which is assumed to be locally tetrahedral. So it forms like this kind of small pyramids locally. And by viewing water from this perspective, you can actually explain a lot of these anomalies. So this idea comes naturally when you look at the water's phase diagram, where you have here temperature and pressure. And up here you have the stable water. Here, this dashed line is the melting line. And below here, you have the supercooled water that I mentioned already. So then as you go down here, you have the glassy water, which can exist in a low density amorphous and a high density amorphous. And now here you see a film that we shoot in our lab. When you take a high density amorphous ice and you just let it on the table and it decompresses. So you see, due to the change in density, it starts to expand We also call it popcorn ice. And you have a change in density that is quite dramatic, actually. It's from nearly 30% or so jump from 1.17 to 20% or so, from 0.94. So it jumps from like something that's very compressed to something that is like it jumps from this phase, from this part here to down here. And now you see there is this kind of white region in the between that's kind of hard to do experiments, because as you come from the glassy state, it crystallizes, and the same is true for the supercooled water. So it's because of the ice that is forming, crystalline ice, it's been termed as a no man's land. So experimental no man's land, because it's kind of between two trenches, so to say. And the hypothesis is that you have down here a kind of phase separation line that separates the low density and the high density amorphous. That then here you have this glass transition. So when you go from the high density amorphous to the high density liquid, and there are some evidence for that. And also the same is true here when you go to the low density amorphous to low density liquid. And the hypothesis is that this kind of phase separation line, this binodal, extends inside the no man's land, and there is a critical point at which it terminates. So if you were to zoom in this region, it looks like this. This is now taken from a review article from Anders Nilsson and Lars Petersson, with who we work with. So this is temperature and pressure. And here is this phase coexistence line and the critical point. And then you have a low density liquid and a high density liquid, which is hypothetically macroscopically. So you can even have a whole glass of low density liquid and a whole glass of high density liquid. And then as you go past this point, you enter what is called this anomalous region, where the phase coexistence line extends into, it's no longer a sharp boundary where you have a phase transition, but it's more like a soft transition, like a Widom line, where instead you have like this kind of domains that are forming. So you have, for example, like you see here, you have a high density liquid and you have low density islands forming. And the reverse is here. Some people might be familiar with this concept from the magnetic domains, for example. It's a similar concept, that you have like kind of regions that are forming. And the point is now, as you cross this Widom line, you cross over from something that is dominated from high density liquid to something that is dominated from a low density liquid. And there are actually some recent experimental evidence. This is based on some experiments we did in SAC lab, in PAL XFEL, by using this technique, which is called evaporative cooling. So in this evaporative cooling, essentially, what you do is you insert water droplets in vacuum. And as you see here, the water molecules are flying off. And by rapid evaporation, you have very fast cooling, basically. So that's a way that you can look at liquid down to 229 Kelvin. And by fast cooling and by shooting each of these droplets individually with an X-ray pulse, you can still pick up some liquid, because statistically, you may end up in the situation that you have most of the droplets are frozen, but some of them are still liquid. So statistically, you can find a few rare cases that you can still maintain the liquid. And then because of the capabilities with the X-ray lasers, you can measure the X-ray pattern. In this case, the small angle X-ray scattering and the wide angle X-ray scattering. And with this, we were able to get some kind of information on the correlation length. There are other quantities also that were measured there. For example, here is shown in blue is shown in D2O, and that shows a maximum around here. And in red is shown for H2O. And in the inset, you can see a bit more extended the whole temperature range that we measured. But it does show a maxima, as we expected, around the Widom line that I was explaining, that you cross over from from an environment that is dominated from a high density liquid to one that is dominated from a low density liquid. So in these experiments, we looked at basically thermodynamic and structural properties. And the question now was, can we also do something to get information about the dynamics? That's kind of the starting of my presentation. So we went to LCLS, and some of you are familiar with this, where you have the linear coherent light source at SLAC in California. And we measured we attempted basically to measure the dynamics using this approach at the XCS station, X-ray correlation spectroscopy station at LCLS. So let me explain a little bit the experiment, the concept of the experiment. So the idea is like this. We want to do an ultrafast XPCS, so X-ray photon correlation spectroscopy. So the idea is, if you had, let's say, a camera that was fast enough, and you took a photo of the water molecules in real space, you would get something like this. With X-rays, you're mainly with hard X-rays, you're mainly sensitive to the oxygen, because that's when you have the most electrons. The hydrogens are almost invisible. So you would get something like this. And if your camera was fast enough, had a fast enough shutter, you would see the molecules standing still. We don't do an imaging experiment. We project this instead in reciprocal space. So in reciprocal space, what you get is something that looks like this. This is actually from a simulation. Well, we calculated the speckle pattern. This is what we call a speckle pattern. This arises basically from, you have the X-rays coming, scattered from your molecules, and there is an interference. So this is essentially like a 3D interferogram, just like you have from a crystal, but here is a disordered structure. And if your coherence is good enough, then you can actually record the interferogram, the 3D interferogram from this structure. So if you, let's say, change the exposure time of your camera, you would get something that is a bit blurred out, right? Just like trying to take a photo of a baby that is constantly moving. The same is happening here, but we are actually recording this in reciprocal space. So we are essentially going towards the time average limit, which you get from your static XRD machine. And you get something that is more azimuthally homogeneous, and you start to blur out essentially this interferogram. And then when you go at even longer times, essentially the image is completely blurred out, and what we call the speckled contrast is also completely blurred out. It looks very homogeneous. So that's the idea. And instead of having a camera, of course, we use the X-ray laser. So here like I mentioned, we use this evaporative cooling approach, where you have a droplet that you insert these droplets in vacuum, and as they travel, they're rapidly cooled. And by varying the travel time, you can vary the temperature, essentially. So then you come in with your X-ray pulses, and that's when you basically can vary the time. You can vary the pulse duration here. So by varying the pulse duration, you can change the exposure time, and then we use two detectors. One is the CS pad, one is like at a very close sample to detector distance, in order to record a very broad Q range, which allows us, for example, to say that whether a droplet is frozen, or if it's in a liquid state, or if it's a miss. We had a lot of misses as well, where we didn't hit the droplets. And then a second detector at a large sample detector distance, in order to be able to record this speckle pattern, because it's important that depending on the pixels that you're using, to be able to match the speckle size in order to see the interferogram. Otherwise, you're losing the contrast information. So this was about 1.5 meters or so, this distance. So now again here, the same concept. As we have a very short pulse, you can record a very clear interferogram. As you make your pulse longer, this becomes blurred out. Okay, this looks very nice on this cartoon that I'm showing here. In reality, it's actually much more messy, as you will see in a second, and because there are a couple of challenges actually. So this challenge challenge number one is that water is a very weak scatterer in the hard X-ray range. Here we used 8.2 kV. So here I define the concept of the mean photon density, which is essentially how many photons you have on your detector divided by the number of pixels. So here you see, for example, if you have 10 photons per pixel, your speckle pattern looks quite nice, I would say. When you go down to 1 photon per pixel, it starts to look a little bit like kind of noisy, but still you can see that there are speckles, right? Whereas if you go down to 0.1 photons per pixel, means that you have 1 photon per 10 pixels, it starts to look like, am I really measuring something, or is this the electronic noise? Well, the experiment we did was actually 1 order of magnitude below that, so at 0.01 photons per pixel, which when we first look at it, you're like, oh, okay, that's kind of hard to say. Is this real noise, or is it just speckles? So challenge number 2 is related to the contrast, the speckled contrast. So in the wide angles, this is actually quite low. We're measuring at the 2 inverse angstrom, 1.9 inverse angstrom, because this is where we are interested to look at the atomic length scales at the water peak. So here is shown now the speckle contrast as a function of Q. And you can see now what the pictures I was showing you before was when you have 100% contrast, or let's say 1. When it drops to approximately 10%, then the best you can resolve is, let's say, a starting point of 10% or so. So anything else that is blurred out from the dynamics is going to be below that. So this is kind of the maximum that you can have. So not only you have something that has very few photons, but also is already very blurred out because of the limitations in the transverse coherence, for example, in this case. This has to do with the limitations in the transverse coherence, because as you scatter your sample, this we're measuring at a very wide angle. So this will be limited depending on the wavefront. So that sounds kind of impossible, but actually people have done experiments before us at LCLS. And this is this paper here, this PRL from 2012, where they showed that it is possible actually to distinguish between shot noise and speckles. And the method that was used there was what's called the negative binomial distribution. So this is a distribution that essentially mathematically, it's a convolution of a Poisson distribution that is used to, shown here in red, which is essentially mimics the shot noise, the noise that you have because of the quantum noise, so to say, because of the reading out the single photons due to the interferogram, convoluted with a gamma distribution that is essentially modeling the speckle intensity distribution. So here, this is this mathematical expression, which essentially has this K bar that I was mentioning just a moment ago, this photon density, essentially number of photons divided by the number of pixels. K is the same, but per pixel basis. And M is related to the speckle contrast. So it's 1 over the speckle contrast. And this is called number of modes. So here you see there's a probability distribution and the incident photon density. So this is basically how the intensity is distributed on your detector. If it looks like the blue curve, is when you have speckles. If it looks like the red curve, it's when you have noise. And by fitting that, we were, with the help of these two guys, TJ Lane, who was at SLAC at the time, but now he's at DAISY, and Felix Lemkuller from DAISY, we were able to get out a contrast of approximately 7%. And now here you can see the running average, and the cumulative average is the red, and the blue one is the running average. So this for us is a big deal, so to say, because it tells us already that, okay, we can at least see the speckles somehow. So now what happens when we change the pulse duration? To do that, we had to basically have some kind of way to read what is the pulse duration on a single shot basis, because as you know, at the FEL, sometimes you say, okay, can I have a pulse duration of 15 femtoseconds or so? but you get the distribution, and that's what is shown here. So we were calling at the people upstream at the control room, and then we get the distribution of 15 femtoseconds. Then we call again, we say, can we get 50 femtoseconds? It gives you a certain distribution. That depends a little bit on the FEL and on the day as well. So, but this, using this basically the XTCAV, we were able to get on a single shot basis what is the pulse duration. And you can read this paper here if you want to know a little bit more about how this works. But essentially it works by not reading directly the photons, but by reading the electron pulse duration. Okay, so now by changing the pulse duration from 20 femtoseconds to, let's say, almost 120, we saw that the speckle contrast was going down, was being decreased, and that was true for 2 different temperatures. And then we also looked at a fixed pulse duration, 75 femtoseconds, and we varied the contrast. And now here is normalized at the contrast at time 0. So we saw that there was a decrease as you increase the temperature. So these are like the 2 main observations we have. We have the time dependence and we have the temperature dependence. And we wanted to understand what is behind this. So this, we did molecular dynamic simulations with my collaborator Gaia Kamisaska, who is now at Rome University. And we looked at 2 different models. One is in a pure ballistic motion. Actually, Gaia was also working with Claudio, if I'm not mistaken, in the past. So we did one model. Is that right, Claudio? She was in your group at some point. Yeah. So we did a pure ballistic motion, measuring like here. It's assumed basically in this model that what we measure is only due to thermals. So it's just pure heat. It's just thermal fluctuations following the Maxwell-Boltzmann distribution. And the rate, the time constant that we observe is proportional to the momentum transfer in this case. Whereas a bit more sophisticated treatment was using molecular dynamic simulations, because this includes the fact that you have hydrogen bonds forming on these time scales. And here you see also, you can also make beautiful images out of them, where you can see what happens in this 120 femtoseconds, where there is a kind of rumbling and moving of the water molecules. And we use the 2 force fields. One is the T4P 2005, and the other is the MB pole, a bit more sophisticated. And the results look like this. So this is now the comparison between the simulation and the experiment. And we see the ballistic is way faster than, so there is some agreement for earlier times, but then it deviates after 25 femtoseconds or so. Whereas the molecular dynamics seems to do a pretty good job. MB pole may be a little bit closer to the experiment. Here you see the dashed line is the T4P and the solid lines is the MB pole for the 2 different temperatures. And in addition, the temperature dependence is interesting, because in the ballistic, it's again way faster. So here we are keeping a constant temperature, a constant pulse duration. And you see that for the ballistic, the contrast would have decayed much more. Whereas for the simulation seems to pick up very well around room temperature, although the slope is slightly different than the experiment. So this is something we are currently wondering, why is this about? We have 2 possible explanations. One is related to experimental reasons, actually. That's something that recently came up in my mind, that it could be that because we cannot establish with absolute certainty the contrast due to some kind of, there is a step involved in the analysis that has to do with converting from analog to digital units to photons. And that introduces a small discrepancy there in the contrast. So this could be one reason. The other reason could be that this is actually due to limitations in the simulations. So that lots of these force fields are tuned for room temperature, whereas if you go to lower temperatures or higher temperatures, they start to deviate. And this is something that is observed, for example, for the specific heat capacity as well, that is related to fluctuations, just like we're looking at here. So they saw a singular trend there. So the take-home message here from this part of the presentation is that we are looking at a kind of regime between the pure ballistic motion. Here is shown the intermediate scattering function as a function of t. Between the pure ballistic motion, where you have like the water molecules moving independent from one another, like an ideal gas, and the later diffusive regime, where they are kind of shuffling in with their neighbors. This between regime, it's basically when you go to the supercooled, when you go, it starts to exhibit a kind of plateau that relates to the cage effects, to the presence of like a kind of transient trapping that is happening to the water molecules by their neighbors, that becomes more pronounced when you go to supercooled states. And then from the simulation, polarisability seems to play a role, but also many bad interactions. Okay, so this now this now brings me to the second part. After this beam time, actually, I think it was exactly right after this beam time. It was when we had another beam time at SDAQS, and we flew there. Here you see now in Japan. Here you see Spring 8, the facility, the synchrotron, and the SDAQS, the XFEL. And up here you see the Pico, who is the mascot of SDAQS. There's actually some quite funny videos if you look up online. So there we wanted to look at using X-ray scattering to look at the orientational dynamics. So Pico, the mascot here, will help me to explain a little bit how this experiment works. So this is what we are doing, optical Kerr effect using XFELs. So if you have, let's say, your X-rays coming in and a liquid sample filled up with picos, and they are kind of randomly oriented, you will get a scattering pattern that is isotropic. So for all angles, you will get the same signal. If you exclude, let's say, the speckles here now for a second, here this is kind of an incoherent experiment. Whereas if you have a pump pulse that comes in this case we use an 800 nanometer, that due to the electric field induces a dipole on Pico and makes these guys align, then you will get a kind of increase in intensity along this axis and a decrease in intensity along this axis. So you will get an anisotropic pattern. And by basically following as a function of the pump probe delay how this anisotropy disappears, you can get information about the loss of alignment, of orientation in this system. So that's the concept. And we did the same with water molecules. And here we used 12 keV photons, an 800 nanometer pump. And we looked at the anisotropy, like I explained, by taking the difference between the parallel, now parallel to the polarization, minus the perpendicular. So that's how the signal looks like. It has a negative and positive signal, which is related to the difference, basically. And this was done, of course, you should say here, it was done in collaboration with my colleague Kyung-Hwan Kim, who was at the time at Stockholm University and now is assistant professor in Postec in Korea. But we are still collaborating on this project. So,
sorry, Foivos.
Yeah.
A small technical question. Here you put arbitrary units, but what is the relative difference between the two maximum and minimum?
I will answer this in the next slide where I show, I can answer it, let's say, in comparison to the heating signal, which is the isotropic. I will come back in the next slide. If it's still a question, we can discuss about it. This is like a little bit the experimental parameters. So here we use larger jets. The droplets here are, the jet is a continuous, the droplets about 80 microns. The pump is, like I mentioned, 800 nanometers. The probe is 12 kV, and we use the time tool here available at SDAQS that allows us to get a very good time resolution. For the analysis, we have about 1,000 images per delay. And for the anisotropy, like I mentioned, we take the difference parallel minus perpendicular, meaning with respect to the polarization. And for the heating, now I will come to your question, Claudio. We take a difference between laser on and laser off. So this is now something that probably you have seen before, the heating signal. So here I show now again, this is an arbitrary unit, but in relative, let's say the anisotropy here is shown on the left and the heating shown on the right, their axes are comparable. So there's been an offset that has been introduced. So you see now here, anisotropy is for negative time delays. So to say time zero, before time zero, looks pretty flat. Then you have this characteristic signal at 40 femtoseconds. Then it decays already at 400 femtoseconds or so, and at 1 picosecond is again flat. And then on the right here, you see the heating signal, which is approximately 0.1 Kelvin. So that's actually a way to make these arbitrary units into something meaningful, saying that the heating that we see you see the signal is evolving at a slower time scale, it evolves in the approximately 1 picosecond or so time scales. And you can see now already from the noise that this looks larger, but also you can see it from the relative. So it's almost a factor of 3 or so larger than the anisotropy signal. So I think this somehow addresses your question. It's difficult to put real units there because it depends on many parameters, such as the scattering intensity, jet thickness. In principle, one could do this as a cross-section and so on, but I think it's safer to just say on a relative scale, you see with respect to the heating is a factor of 3. And here is now the dynamics. So you have the anisotropy that rises and then drops very fast, initial drop of approximately 160 femtoseconds. And there's a slower component actually here on the picosecond time scale. And then you have the heating that rises at slower time scale. So you can clearly separate those two. And so in order to understand this, again, we did some molecular dynamics simulations. Here, now you see the comparison between the experiment and the theory. And the theory that Kyung-Hwan was responsible for, he used this polarizable force field with an explicit electric field. And it seems to agree pretty okay, I would say, without any tuning or any other parameters, which gave us confidence. And then we decided, okay, one other thing we can get at is how, for example, the anisotropy decays inside the simulation by looking at the dipole, the angle between the dipole and the electric field. And this we define as theta. This is this angle. And then here you see the cosine squared theta minus 1/3. The reason we use this kind of definition is that when the sample is completely randomized, this R is equal to 0. When it's parallel, aligned along the electric field, it becomes positive, and it's perpendicular, it becomes negative. So here we see that just like in the experiment, we have a sharp rise shown in blue here and a decay. And then when you convolute it with the instrument response function shown in red, it shows a quite good agreement with the experiment, that in the sense that there is this fast component followed by a slower component. So then we took one step more in the simulations and looked at the radial distribution function. So the radial distribution function of the oxygen-oxygen molecule. So that tells you basically what are the distances between one reference water molecule and its first neighbors, the first coordination cell, shown here in this cartoon. And you can see there's a distribution of distances, and then you can also do that for different time delays. So it is interesting because it seems like if you look here, there is a small shift in this distribution, And it becomes more clear if you take the difference between the different times with respect to the time zero. So this difference tells you that there is a small contraction that is happening. When you excite the molecule along this polarization, there seems to be a small contraction for a very short time. And we also looked at the second coordination cell. This is now the peak on the second cell at what happens, which we know it's more sensitive to this tetrahedral distance here, this 4.5 distance. And there it was actually not such a pronounced difference. It was mainly the amplitude that's changing, that we attribute, and it comes also at a slower time. So we attribute this to heating actually, because we know if there is a heating, that will be a change in the second coordination cell. That has to do with the fact that you transform from a more low density to high density environment, right? So now we thought, okay, let's try to understand how does this alignment happen when you have low density and high density liquids. And in the simulations, we define this local structure index, which is an order parameter that allows you to separate high density liquid and low density liquid. And this is a good reference here where you can see, for example, at 230, you have a lot of low density shown here in blue, whereas at room temperature, you have more high density. And that's what we did. So we essentially unravel the cosine squared theta, this anisotropic component, into a high density liquid and a low density liquid. And we see that there is a kind of, the amplitude of the low density liquid is slightly larger than the high density liquid, which indicates that the low density liquid is probably easier to align. And they show a similar decay. It's a bit noisy, but they kind of show a similar time scale. Whereas the same is true if you look at the difference in the radial distribution function. Here now is shown again for the high density and the low density liquid. And the high density liquid has a much larger amplitude here. So you can see now that, again, this indicates, the low density liquid has a larger amplitude. This again indicates that the low density liquid is more susceptible to alignment than the high density liquid. Now, why is that? One way to explain that is you can think that low density liquid has stronger hydrogen bonds. And that, as a result, makes it to have a more delocalized wave function of the electronic structure, as shown here in this cartoon. Which then you can think that when you come in with the electric field, and this is easier to induce a dipole. There are more susceptible, which then couples to the rotational degree of freedom, so which induces the rotation. So it makes it more susceptible to the alignment. So these are interpretation at the moment. It would be interesting to have some follow-up experiments and to measure it deeply supercooled with this method. And that's something we're hoping to do in the future. So the take-home message here is we did this kind of pump probe experiment where you come in with 800 nanometers. You induce an alignment and you probe with X-rays that appears on anisotropy in your detector. And then we see that the low density liquid seems to be easier. The parts in the water that is low density seems to be easier to align than the high density, or let's say more susceptible to alignment. Okay, so this takes me now to my outlook. So, like I mentioned, we would like to go a little bit further with this in the future and measure as well protein dynamics. So actually next week we have a beam time at the European XFEL remote to try to do this kind of experiments with XPCS on proteins, at highly concentrated proteins, and get some kind of information about the time scale of the motion in the proteins. But it would also be interesting to measure further supercooled water and not just capture the initial drop like we measured in this experiment that I mentioned, but measure the full G2 function, the full range. And that would allow us to look also at this diffusive part that seems to change quite a bit when you go in the supercooled regime. And with that, I would like to come to the acknowledgement slides. So first of all, I would like to thank my group, which is in structural dynamics of aqueous solution in the physics department, as well as my collaborators, Anders Nilsson, of course, we've been working together on these projects, Katrin Amman-Winkel and Gaia, who did the simulations, and as well as collaborators from University of Siegen, Christian Good, from Postec, from Kyung-Hwan Kim, and SLAC, the guys from SLAC and DAISY, and as well as from SACLA. And here is the funding, which was from Swedish Research Council, European Research Council, etc. Thanks for your attention, and I'd be happy to answer any questions.